side as Institute of Engineering and Technology. Today we are going to discuss few more topics of sequence and series. So let's begin with the first topic, that is infinite series. So if we add the terms of an infinite sequence un from 1 to infinite, then the expression we will get is u1 plus u2 plus u3 plus up to un and plus so on, which is an infinite series. So for example, if we have the sequence 1, 2, 3 and so on, right? This is an infinite sequence, and if we add the terms of sequence, so you will get an infinite series, right? Now let's discuss its notation. If the series is infinite, it is denoted as summation n from 1 to infinite un or simply summation un. And if a series is finite, it is called a finite series, and it is denoted as summation ui I runs from 1 to n. This is the series of first n terms. Okay, now let's discuss partial sum. If series un is an infinite series, then the partial sum is denoted by Sn, and it is defined as S1 is equal to U1, then S2 is equal to U1 plus U2, partial sum of first two terms, then S3, that is U1 plus U2 plus U3, partial sum of first three terms, then S4, that is U1 plus U2 plus U3 plus U4, partial sum of first four terms. So similarly, you can get Sn in general as a sum of first n terms, that is u1 plus u2 plus u3 plus up to un. Also we can write as summation ui I from 1 to n. Okay, now this partial sum will form a new sequence of Sn. Okay, now let's discuss the another topic, that is convergence and divergence of an infinite series. So firstly we will discuss convergence series. So the series un is convergent if this Sn is what? It is the partial sum of first n terms. Okay, so if this Sn tends to a finite unique limit S as n tends to infinite, then we can say that this series un is convergent series. Okay, and we will denote it as limit n tends to infinite Sn is equal to S. This S is a finite term. Now S is called the sum of the series. We can write as series un is equal to S. Next, divergent series. The series un is divergent if Sn is partial sum of first n terms. If Sn tends to plus or minus infinite or limit does not exist. Okay, then we can say that this series un is divergent. Okay, so what we have to do is we have to find the limit of Sn. If it is a finite limit, then the series is convergent. Okay, and if it is infinite limit or if limit does not exist, then the series will be divergent. Okay, now let's discuss oscillation of an infinite series. So the series un is oscillatory if Sn does not tends to a unique limit as n tends to infinite. Okay, so whenever the limit of Sn is not unique, then we can say that this series un is oscillatory series. Okay, so now we will discuss the properties of series. If series un and series vn are two convergent series, then series cun, series un plus vn and series un minus vn are also convergent, and this we can write the series cun as C series un. We can take this C, that which is a constant term, out of the summation. Also series un plus vn can be written as series un plus series vn, and series un minus vn is equal to series un minus series vn. Removal or addition of finite number of terms does not affect the convergence of a series. Okay, so on removing or addition of a finite number of terms, this convergence of series will remain same. Okay, next, begin with the example. Here we have to prove that this series n square is divergent. So let's begin with the solution. Here un is given, that is n square. So first we will find Sn, that is partial sum of first n terms. So 1 square plus 2 square plus 3 square plus up to n square. Now we know this summation as n into n plus 1 into 2n plus 1 upon 6. Okay. Now we will apply limits. So limit n tends to infinite, Sn is equal to limit n tends to infinite. Write down this answer of Sn. Okay. And if you will apply limit n tends to infinite, you will get answer infinite. Right. So this limit of Sn is infinite. Therefore, we can say that the series is divergent. Okay. Now, next example. Discuss the convergence of 1, minus 1, plus 1, minus 1, plus 1, minus 1 and so on. So, here un is given, that is minus 1 raised to n plus 1. Okay. Now, firstly S1. So, you will get here 1. Next S2. So, partial sum of first two terms. You can see from here also 1 minus 1. So, it is 0. Then S3. So, partial sum of first three terms. So, from here 1 minus 1 and plus 1. Okay, which is 1. Similarly, S4, it is 0. Okay. So, in general, whenever we have S2 and for even terms partial sum, it is 0 and odd terms partial sum is 1. Okay, so what we can say here, the limit is not unique, right? Whenever limit is not unique, what we can say that the series is oscillatory. Okay, now let's discuss one more example. Discuss the convergence of a series tan inverse 1 upon n square plus n plus 1 and find its sum if possible. So, here un is given, that is tan inverse 1 upon n into n plus 1 plus 1. Now we will take this n into n plus 1 common. So what you will get, tan inverse 1 upon n into n plus 1. So here we have 1 plus 1 upon n into n plus 1. Okay, now we will rearrange this 1 upon n into n plus 1 as 1 upon n minus 1 upon n plus 1. Okay, and this denominator we have kept as it is. You can here cross multiply and check, so you will get this term. Now we know this formula, that tan inverse x minus y upon 1 plus xy. This is equal to tan inverse x minus tan inverse y for mod xy less than 1. So we will apply this formula here. So this is your x and this is your y. Okay, so you will get un as tan inverse 1 upon n minus tan inverse 1 upon n plus 1. Okay, so we will find Sn, that is partial sum of first n terms. Also we know this un is what, tan inverse 1 upon n minus tan inverse 1 upon n plus 1. Okay, so firstly for n is equal to 1, so you will get u1 as tan inverse 1 minus tan inverse 1 by 2 plus, now we will write u2 for n is equal to 2. So you will get tan inverse 1 upon 2 minus tan inverse 1 upon 3. Okay, then u3, that is for n is equal to 3. So you will get tan inverse 1 upon 3 minus tan inverse 1 upon 4 plus so on, and nth term, that is tan inverse 1 upon n minus tan inverse 1 upon n plus 1. Now this tan inverse 1 by 2 will get cancelled, this tan inverse 1 by 3 will get cancelled. Okay, so at last what will remain is this first term, that is tan inverse 1, and this last term, that is tan inverse 1 upon n plus 1. Other all the terms will get cancelled. Now we will apply the limit. So limit n tends to infinite, Sn is equal to limit n tends to infinite tan inverse 1 minus tan inverse 1 upon n plus 1. Okay, now we know the answer of tan inverse 1, that is pi by 4. And if you will apply limit here, so you will get tan inverse 0, which is 0. Okay, so simplify, so you will get answer pi by 4, which is a finite term. Okay, so we can say that the given series is convergent, and this is your small s, that is sum. So this sum is what, pi by 4. Okay, now Another example, discuss the convergence of geometric series a plus ar plus ar square plus ar cube plus up to ar raised to n and so on. We can write in the form of summation as summation n from 1 to infinite a r raised to n minus 1, where a is not equal to 0. So let's begin with the solution. Here we will start considering r is equal to 1. Okay, so you will get Sn as here in place of r, if you will write 1, so you will get a plus a n times. So we will write it as n a. Now as n tends to infinite, this na will also tends to a plus or minus infinite. Okay, so this limit of Sn is plus or minus infinite, right? Therefore limit does not exist, and we can say that the series is divergent for r is equal to 1. Now we will take r not equal to 1. So what we have is Sn, that is this a plus ar square ar cube plus up to ar raised to n minus 1. Okay, so this is the partial sum of first n terms. Now we will multiply r with this Sn. So you will get ar plus ar square plus ar cube plus up to so on ar raised to n minus 1 plus ar raised to n. If you will multiply r here, so you will get last term as this ar raised to n. Okay, now we will subtract this Sn minus rsn. Okay, so we will subtract this. So this ar will get cancelled, ar square will get cancelled. At last, what will remain is this a and ar raised to n. Okay, you can see here. Now we will take a common from here. We will take Sn common and make Sn as a subject. So you will get Sn is equal to a into 1 minus r raised to n upon 1 minus r. Right? Now r is between minus 1 to 1. Then we know that r raised to n will tends to 0 as n tends to infinite. Okay? So apply the limit, so you will get limit n tends to infinite. Sn is equal to limit n tends to infinite. Write down this Sn. Okay, now first we will split it. So you will get a upon 1 minus r minus a upon 1 minus r into limit n tends to infinite r raised to n. Now we are considering r between minus 1 to 1. So this r raised to n will tends to 0 as n tends to infinite. Okay, so this term will be 0. So what remains is a upon 1 minus r. Okay, so which is a finite term. So we can say that the geometric series is convergent when we have mod r less than 1. Okay, and its sum is a upon 1 minus r. And for r less or equal to minus 1 or r greater than 1, then the limit r raised to n does not exist. Okay, and so this geometric series is divergent for r less or equal to minus 1 or r greater than 1. Okay, so now we will summarize this whole geometric series. So geometric series is given by this form, that is a plus ar square plus ar cube and so on up to ar raised to n. Okay, and we can write it as summation n from 1 to infinite ar raised to n minus 1, and this a is not equal to 0. So what is the conclusion? That the series is convergent if mod r is less than 1 and its sum is what? A upon 1 minus r. The series is divergent for mod r greater or equal to 1. Okay, so you have to remember this while solving the sum of geometric series. So let's begin with the example. Prove that 1 plus 2 by 3 plus 4 by 9 plus 8 by 27 plus so on is convergent and find its sum. So the solution. Now we will write this all terms as 1 plus 2 by 3 plus 2 by 3 whole square plus 2 by 3 whole cube and so on. Okay, and we can write in the form of summation as summation n from 1 to infinite 2 by 3 whole raised to n minus 1. Now this is a geometric series with the ratio 2 by 3, okay, which is less than 1. Now we know the condition that if mod r is less than 1, then the series is convergent, right? So this series is convergent, and now we have to find its sum. So its sum will be s is equal to a upon 1 minus r. A means first term, that is 1, and common ratio r, that is 2 by 3. Okay, so just substitute the answer of A and R and simplify, so you will get answer 3. Okay, next. The figure shows the first 7 sequence of square. The outermost square has an area of 4 meters square. Each of the other square is obtained by joining the midpoints of the sides of the square before it. Okay, yes, so here you can see the sequence of first 7 square. This is the first square. Okay, its area is given, that is 4 meters square. Now this second square is formed by joining the midpoint of this first square. Okay, similarly this square is formed by joining the midpoint of this square, right? And we have to find the area of the all square in infinite sequence. Okay, so let's begin with the solution. Since each square is obtained by joining the midpoints of the square before it, so the area of the square is half the area of the previous square, right? So area of second square is equal to half area of outermost square. Now we know the area of outermost square is 4. Okay, so you will get area of second square as 2. Now area of third square is equal to half area of second square. Now the area of second square is 2. So the area of third square will be 1. Okay, so you will get the sum of areas of all square in infinite sequence as S is equal to area of first square, that is 4 plus 2 plus 1 plus 1 by 2 plus 1 by 4 and so on. Okay, now take 4 common from this. So you will get 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 and so on. Right. So now this is a geometric series. We can simplify it like this. Right. That is 1 plus 1 by 2 plus 1 by 2 whole square plus 1 by 2 whole cube and so on. So here the first term is A, that is 1. R is 1 by 2. Okay. So which is less than 1. Right. So it is convergent. So we can find its sum. So its sum is what? A upon 1 minus R. Okay. Here we have to multiply it by 4. So 4 is taken already. Right. A is here 1. So 4 into 1 upon 1 minus R. R is 1 by 2. Simplify this. So you will get answer as 8. Okay. Next. Discuss the convergence of geometric series 2 raised to n plus 5 upon 3 raised to n. So let's begin with the solution. Here, series is given, that is 2 raised to n plus 5 upon 3 raised to n. Firstly, we will split them. So you will get 2 upon 3 whole raised to n plus 5 we have taken out. So 1 upon 3 whole raised to n. Next, series 2 upon 3 whole raised to n plus series 5 into 1 upon 3 whole raised to n. Next, we will write this by substituting n is equal to 1, 2, 3 and so on. So you will get 2 by 3 plus 2 by 3 square plus 2 by 3 whole cube and so on. And similarly here also, so you will get 1 by 3 plus 1 by 3 square plus 1 by 3 cube and so on. Okay. Now both the series are geometric series. Okay. And the ratio of this series, that is R1. So it is 2 by 3. Okay. And the ratio of this series, that is 1 by 3. Okay. A1 it is 2 by 3 and A2 is 1 by 3. Okay. So now we will apply the formula. Also, this mod R1 is less than 1 and R2 is also less than 1, right? Therefore, both the series are convergent. So we can find its sum. Okay. So S1, that is the sum of first series, that is A1 upon 1 minus R1. That is 2 by 3 upon 1 minus 2 by 3. Simplify, so you will get answer 2. Now we will find the S2, that is sum of second series. So A2 upon 1 minus R2. So you will get 1 by 3 upon 1 minus 1 by 3. Simplify, so you will get answer 1 by 2. Okay, now, so the total sum S is equal to summation 2 raised to n plus 5 upon 3 raised to n. Okay, so this we have split like this. Now the answer of this series is 2 plus 5 we have kept as it is, and the answer of this series is 1 by 2. Okay, simplify this, so you will get answer 9 by 2. So I hope you have understood in this session. Thank you for watching.